today we start with companion form of modeling, which is also called as controllable canonical form. So, in this we will going to study introduction to companion form, that is called controllable canonical form, then mathematical representation in state space form and numerical example. Now, about the introduction to companion form of modeling. As last class we have seen that any system can be represented in a state space form, and in that case we are considering different physical variable. But sometimes what happen, if you are written the equation in differential form or if you have a transfer function form, then in that case how will you get the state space model? So, there are different methods are available to convert the given system into state space form, or we can say there are different forms are there, that is called companion form, canonical form. In a companion form there are two types, that is called controllable canonical form and observable canonical form. Then there are other method in which the given system has been converted into a canonical form. In that canonical form there are particularly diagonal canonical form and Jordan form. Now, about the controllable canonical form, what is the importance of this particular form? The main importance of this form is that is very simple in nature. In this case what we have to consider as output as a first variable, and remaining variables are the derivative of the output, and if you do this one we can easily get the state space model. So, that means here the companion form of modeling is called phase variable form. They can be easily determined if the system model is already known in the differential equation or transfer function form. Third point, they are defined as a particular state variable which are obtained from one of the system variables and its derivatives. Often variable is selected as system output and remaining variables are the derivative of the output. This is the basic concept. That means what we have to do here, we have to take output as a first variable and remaining variables are the derivative of the output, that is the strategy. Now, we have to represent the given system in a state space form. So, state space form is, we want the system to be in this form: x dot equals to ax plus bu, y equals to cx plus du, this we want. So, now to get this form we first of all write a differential equation. So, that equation is nth order differential equation. So, we write this nth order differential equation as dny by dtn. So, here nth order differentiation of y plus a of n minus 1. Now, differentiation, so n is there, we write n minus 1 dt of n minus 1 of y plus, and this process we repeat it, plus we write a1 into dy by dt plus a0 into y, that is equal to, so this function we can write equal to bn plus differentiation of n of dt n u plus b of n minus 1 differentiation of n minus 1 dt of n minus 1, and this process is repeated, plus b1 into du by dt plus b0 into u. So, this is your nth order differential equations. Now, in this case this a1, a0 are the variables, here also there are some variables. Now, these equations or this differential equation we have to write down in a state space form. Now, here we are considering two cases. The one case is that there is no differentiation terms involved, that is all the differentiation terms in the output we have to make 0, that means these terms I want to make 0. The derivative of u we will make 0, only this form is present, this form is present. So, what is this type of system? That means if you write in the transfer function, let us say I can write transfer function as ys by us equal to s square plus 2 by k. So, k divided by s cube plus 3s square plus 2s plus 1. Now, this is the part I have written. Now, here what we are doing here, I am removing this s square part, only constant part we are keeping. Okay. So, now your equation is this one, d raised to n dt n plus a n minus 1 d of n minus 1 dt n minus 1 up to a 0 y equals to b 0 into u. Now, we go for our strategy. So, our strategy says you have to consider output as a first variable. So, when we say output as a first variable, so here output is your y, your output is y. Now, first variable we can write here x1 equals to y. So, x1 equals to y is our first variable, and now what our says, remaining variables are the derivative of the output, remaining variables are the derivative of the output. So, what we can write now, another variable is x2, we can write as dy by dt, this is differentiations, that is equals to, so we take it is x1 dot. So, x2 equals to dy by dt equals to x1 dot. Now, about the remaining variable, so remaining variable I can take another one variable x3, x3 is d square y by dt square. So, now here there is nothing but equals to x1 double dot, that is equals to x2 dot. So, now here x2 dot equals to x3, x1 dot equals to x1 equals to y. Now, this process we can repeat it. So, x2 3 we can write now here xn. Now, this xn equals to, so here 3 reduced to 2. So, we write d of n minus 1 y dt of n minus 1. So, that is equals to, let us see here 3 reduced by 1. So, here we can write down as x n minus 1 dot, the xn equals to x minus 1 dot, and similarly now we have to write xn dot. So, what is xn dot? Xn dot equals to dny of dt of n. Now, finally, we have to represent these equations in a state space form. Now, here xn dot we are written. Now, we what we have to write, this is dn by y dtn. Now, here xn dot, this xn dot equals to, we can write this equation as a n minus 1, and what is differentiation of n minus 1 dt of n minus 1 is given as, that is equals to xn, this is minus, then minus, because if you move this side, a of n minus 2, x of n minus 1, and this process is repeated, and finally we will get here minus a1, see here a1 dy by dt. So, dy by dt equals to a1 x2 and minus a0 into y, y is x1, and this part we have kept 0, you just see here, and now we write b0 into u. So, we got xn dot equals to a of n minus 1 xn minus a of n minus 2 x minus n1, a1 x2 a0 x1 and b0 into u. Now, there are variables are x1 dot, you just see here x2 dot, xn dot, and now we have to write in a state space form. So, what is the state space form is x dot equals to ax plus bu. So, we write as x1 dot, x2 dot up to xn dot, that is equal to, now what is x1 dot, your x1 dot equals to x2, just see here this is x1 dot equals to, so we write 0 1 and remaining elements are 0. So, we write remaining elements as 0 1 0 0 0 like this. Now, x1 dot we have written. Now, we coming to x2 dot. What is x2 dot? x2 dot equals to x3. So, it's here x3. So, this is x2 dot x3. So, we write 0 1 0 sorry 0 0 1 0 0 like this, and this process repeated, and now we come into xn dot. Now, here xn dot equals to, see here a0 x1 a1 x2 like this, a of n minus 1 xn. So, what way we can represent this, that is equals to minus a0 minus a1 minus a2, and this process repeated up to minus a of n minus 1, and now here x1, x2 up to xn, plus we write this as 0 0, and particularly xn dot we get here b0 into u. So, this you have x dot, now here ax plus bu. So, b is this one. So, now state equation we are determined. Now, we have to write output equations. So, output is y equals to cx plus du, and in order to write this y, so what is y? Y equals to x1. So, y equals to x1, it means we write as 1 0 0 0, here we can write x1 to xn and 0 into u. So, xy equals to x1. So, this is the state space model we have determined for a given nth order differential equation, and the most important point is that here all the derivative terms we have kept 0. So, the derivative terms are 0 are there, it means that there is no 0 is involved in the transfer function model, only numerator constant and the denominator constant. And therefore, now what we are do, we will take one example and try to solve it. So, for that purpose I have taken a very simple example. I can write as ys by us, this is transfer function model. Now, I have written as 2 s square plus 2s plus 1. This is a transfer function, and you know transfer function, Laplace transform output to Laplace transform input, initial conditions to be 0, we have already seen this transfer function. Now, here we have to write this in a state space form, particularly a companion form, phase variable form, or other words it is called controllable canonical form. Controllable, this is also a word which is common for this type of problem. So, here we want to write its state space form. So, what? So, here we find that 2, so 2 means in order 2. Therefore, the state space model we get having the matrix order is also 2 by 2 cross 2. So, here how many states will take? So, here we take 2 state, x1 dot and x2 dot. Now, here we can write easily the x1 dot, we can generalize from 0 1, this is x1 and x2. So, x1 dot you can find equals to x2, and here b into u. So, here 0. Next, now what is x2 dot? X2 dot, if you see the previous slide, your previous slide is where xn dot equals to a0, a1, a2n, that is if you say these are nothing but the coefficient of the denominator. So, we can write down directly, you will find that we can write down directly minus 1 and minus 2, and here this is 2, b2, this is b. So, this is the state equations. Now, what is the output equations? And here output y as 1 0 into x. So, here we get 0, this is 2, this is bu just here, you got equations b. So, here that is why we written here 2, and here y equals to 1 0 x1 x2. This is a state space model. Similarly, we can take another example also, ys equals to say 10 divided by s4 3s cube plus 2s square plus 5s plus 4. This is a fourth order model. Now, we have to write down in a state space form. How you write? 4. So, we how many state will take? We take 4 state, x1 dot, x2 dot, x3 dot and x4 dot. That is equal to, see here what I am writing down here. So, here x1 dot equals to, so write 0 1 0 0, then second x2 dot equals 0 0 1 0, then here 0 0 0 1, and write the element in the reverse order 4. So, I write minus 4, second we write minus 5, third we write minus 2 minus 3, and again this is x1 x2 x3 x4 plus, and now here 10 coming 0 0 0 10 into u, and output is same, output equals to 1 0 0 0 x and 0 0 into u, because d is 0. So, this is the, we can say, the representation of any system in a state space model. Now, what we have to do here? Now, we have to represent this particular system in terms of a Simulink diagram, because normally all the system we have to analyze through some software. Software means we are using software as MATLAB. Therefore, we have to simulate through an integrators. So, different integrators we have to use. So, how to represent the given system into the state space model, but in terms of Simulink diagram. So, here we have to use the concept of integrator, as I told. So, here when I am saying x1 dot equal to x2, that means here I have used integrator like this, and here x1 dot is there, after integration it becomes x1. Now, we have to represent the given system into a form that is called, that is we can say different integrators are involved. So, how do you do it? So, for that purpose, now what we did, so that we can write here, this is your simulation diagram we can say, not an example, because already example we have already seen, therefore we can write simulation diagram. So, here how many integrators we required? Now, here when the plant is nth order, so we required n integrators. So, therefore, what we are doing here, we are doing integrators. So, what we can do here, I am using first integrator here, this is integrator. So, this integrator is say x1 dot, that is equals to x2, and that is equals to y equals to x1. So, x1 dot, when we integrate we get x1, that is x, and that is equals to x1, and now here we will add another integrator. So, here integrator we use. So, here what we want here x2. So, when we get x2 dot will integrate with this, okay, we will get x2. So, here what we do, x2 dot equals to x3, and this we repeat or move this process like this, and finally, so we are coming to an integrator, that is x of n minus 1. Now, here x minus 1. Now, how we will get x minus 1? That means in this case, when x minus 1 dot integrate, we will get x of n minus 1. Therefore, we write x of n minus 1 dot, that is equal to nothing xn, and now what we look at, we required another integrator here, and now here is xn dot, and now xn dot we write like this. So, xn dot we have seen that is equals to bu. So, we write this is b and this is, because we have seen a previous slide here. So, this is bu. So, here b0 into u, this is, those are this u we have taken here, I can say small bu, and now this xn dot equals to minus a of n minus n xn, then here another one minus a of n minus 2 x of n minus 1, third we write minus a1 into x2 and here minus a0 into y. So, here all x1 dot equals to x2 dot equals to x3 and finally xn dot equals to bu, and whatever equation we have taken here, that has been simulated, and here output y equals to xn. So, this is the Simulink diagram of a controllable canonical form, or it is also called as, we can say, phase variable form. In this case, we will find that there are no zeros are involved, that is, no derivative of the u has been involved. But in real time, zeros play very important role, or derivative of the input plays important role. So, how to develop the state space model of a system when there exist zeros as well as poles? Zeros means what I am saying, that zeros means that derivative of the input. So, how to do it? So, that part we will see in the next class. Now, these are some references. Thank you.